Isaac Newton was born on January 4, 1643, in the small and quiet village of Woolsthorpe, Lincolnshire, England. His birth came into a world of modest circumstances as the posthumous child of Hannah Iskoff and Isaac Newton Sr., who had passed away 3 months before his birth. This absence of a father left Newton in a delicate and uncertain situation from the very beginning, shaping both his early experiences and his emerging personality. His mother, Hannah, would later remarry, leaving young Isaac in the care of his grandmother while she tended to her new household. This early separation instilled in Newton a sense of independence and self-reliance, qualities that would later define his approach to learning and research. From his earliest years, it was evident that he possessed an unusual intensity of mind and an innate curiosity about the world around him. Even as a child, Newton exhibited behaviors and tendencies that hinted at his future greatness. Unlike other children who might have been content with games and social play, Newton spent his time observing, experimenting, and questioning the nature of things. He was fascinated by mechanical devices, often taking apart clocks, locks, and other household objects to understand how they worked. This hands-on approach to learning was not merely play. It was an early indication of the methodical, experimental thinking that would characterize his later scientific endeavors. While some of his contemporaries might have dismissed his obsessions as eccentric, they were in fact early manifestations of a mind determined to understand the world not superficially, but fundamentally. Newton's formative years coincided with a period of great intellectual ferment in England. The country was emerging from the turbulence of the English Civil War, and new ideas about science, religion, and philosophy were circulating widely. The Royal Society in London was beginning to encourage experimental science, challenging long-held Aristotelian notions that had dominated European thought for centuries. While Newton was still a child in a rural village, far from the sophisticated centers of learning, these broader intellectual currents would eventually influence him indirectly, seeding a cultural environment in which radical inquiry and careful observation were increasingly valued. Even at this early stage, Newton's mind seemed attuned to patterns, relationships, and underlying principles, qualities that would later enable him to perceive truths that had eluded generations of scholars. Education in 17th-century England was, by modern standards, rudimentary and often rigid, but it provided Newton with his first formal exposure to the structured world of knowledge. He attended the local grammar school in Grantham, where he received instruction in Latin, Greek, and classical literature. Though these subjects were typical of the curriculum, they were not sufficient to satisfy Newton's intellectual appetite. What truly captivated him were the challenges of mathematics and natural philosophy. Newton reportedly found the standard arithmetic exercises mundane and uninspiring, but he delighted in exploring numerical relationships and geometric patterns. He encountered the works of Euclid and other ancient mathematicians, absorbing principles of logic, proportion, and proof that would become foundational to his own later innovations. One of the most formative influences during Newton's early education came from the books he read and the mentors he encountered along the way. A particularly significant moment was his introduction to the works of modern scientists such as Galileo Galilei and Johannes Kepler. Galileo's investigations into motion and his use of observation and experimentation left a lasting impression on the young Newton, demonstrating that the laws of nature could be understood through careful study rather than mere speculation. Kepler's work on planetary motion similarly revealed that mathematical relationships governed the heavens, an insight that would later inspire Newton's own formulation of the law of universal gravitation. While Newton did not have immediate access to the intellectual hubs of Europe, the dissemination of these ideas through books and local scholars allowed him to begin grappling with profound questions about motion, forces, and the structure of the universe. Newton's personality during his formative years was complex and multifaceted. He was often described as introspective, intensely focused, and occasionally socially withdrawn. These traits sometimes made it difficult for him to form close friendships with his peers, but they also allowed him to cultivate an inner life rich with ideas and imagination. He was known to lose himself in thought for hours, impossibly. This solitary intensity was not merely a quirk of temperament. It was the foundation for a disciplined and methodical approach to inquiry. Newton's capacity for sustained concentration enabled him to develop insights that others, even more formally educated scholars, would have overlooked. His early years were thus a period of quiet but profound preparation, a time in which his mind was being trained to observe, analyze, and question with relentless rigor. A defining feature of Newton's childhood curiosity was his early experimentation with the natural world. There are stories, some more legendary than documented, of young Isaac observing the night sky, tracking the movement of celestial bodies, and speculating about the forces that governed them. He was captivated by phenomena such as the falling of apples, the flight of birds, and the flow of rivers, and he constantly sought explanations that went beyond surface appearances. These early inquiries may seem modest, but they demonstrate the emergence of a systematic scientific mindset. Newton was not content to accept phenomena as mere happenstance. He sought the underlying principles that could explain patterns and predict outcomes. In this sense, his childhood was a laboratory of thought, a period in which he was learning the essential habits of observation, hypothesis, and logical reasoning that would later define his scientific method. The environment in which Newton grew up also contributed significantly to his formative development. Woolsthorpe was a rural area, providing both the tranquility for deep thought and the raw materials for practical experimentation. Newton had access to the countryside, where he could study plants, animals, and physical processes directly. He reportedly constructed rudimentary models, conducted experiments with water flow, and observed the effects of gravity and motion in everyday life. These hands-on experiences reinforced his intellectual inquiries, bridging abstract mathematical concepts with tangible physical realities. In a world increasingly fascinated by the interplay between theory and experiment, Newton's early engagement with both was extraordinarily prescient. Despite the many advantages of his curiosity and intelligence, Newton's early years were not without challenges. The death of his father before his birth, the absence of his mother for extended periods, and the societal constraints of his time could have limited his potential. Yet, these difficulties seemed to fortify rather than hinder him. Newton developed a resilience and independence that became hallmarks of his approach to scholarship. He learned to rely on his own observations, to test ideas rigorously, and to think critically, qualities that would later allow him to confront and surpass the scientific authorities of his day. In this sense, the adversity of his early life was transformed into intellectual strength, shaping a character capable of extraordinary achievement. As Newton matured into adolescence, his abilities became increasingly evident to those around him. Teachers and local scholars recognized his aptitude for mathematics and his capacity for original thought. He was eventually sent to the University of Cambridge, where his early foundations of curiosity, observation, and disciplined study could flourish in a more structured academic environment. Yet, even before his formal higher education, Newton's early life had already laid the groundwork for his future breakthroughs. The combination of innate curiosity, hands-on experimentation, exposure to modern scientific ideas, and the development of an intensely focused, independent mindset provided the foundation upon which his later discoveries in physics, mathematics, and astronomy would be built. In reflecting upon Newton's early life, one is struck not only by his extraordinary intellect, but also by the ways in which environment, personality, and circumstance interacted to shape his development. His early experiences illustrate the importance of curiosity as a driving force, the role of observation and experimentation in learning, and the transformative power of resilience and self-directed inquiry. From the isolation of Woolsthorpe to the books and ideas that reached him from across Europe, every element of Newton's formative years contributed to the emergence of a mind capable of reshaping our understanding of the universe. In examining these early influences, we gain insight into how genius is nurtured, not merely born, and how the combination of talent, environment, and personal determination can lead to discoveries that change the course of human history. As Isaac Newton progressed through his adolescence, his curiosity intensified and expanded into more abstract realms of thought. While his early experiments with mechanical devices and observations of nature laid the groundwork for empirical inquiry, he now began to grapple with the deeper mathematical principles that governed these phenomena. One of the most important developments during this period was his growing fascination with mathematics as a tool not just for calculation, but for understanding the universe. Unlike arithmetic or simple geometry, which could describe quantities or shapes, Newton saw mathematics as a language capable of expressing the underlying laws of nature itself. This insight would later be pivotal, allowing him to frame physical phenomena in precise and predictive terms, a hallmark of his genius. Newton's early intellectual explorations were greatly influenced by the works of classical and contemporary scholars. Euclid's Elements provided a rigorous foundation in geometry, teaching him the principles of logical deduction and proof. Through Euclid, Newton learned to build arguments step by step, ensuring that conclusions followed inexorably from assumptions and evidence, a skill that would underpin all of his later scientific work. At the same time, he engaged with the writings of medieval and Renaissance thinkers who had wrestled with questions of motion, force, and the structure of the cosmos. Though he would eventually surpass them in insight, these texts served as intellectual stepping stones, allowing him to understand where established knowledge ended and where new discoveries could begin. The period also saw Newton developing a fascination with the celestial world. The movements of the moon, planets, and stars were not mere curiosities for him. They were puzzles demanding explanation. He observed how the moon's orbit influenced the tides, how planets seemed to move in elliptical paths, and how comets traced arcs across the night sky. These observations, combined with the mathematical and philosophical frameworks he was studying, began to form a conceptual foundation for his later breakthroughs. Even in the isolated countryside of Woolsthorpe, Newton could envision a universe governed by universal principles, where the same laws applied to the falling of an apple and the orbiting of Jupiter alike. This early recognition of unity between terrestrial and celestial phenomena would later become one of his most revolutionary insights. Newton's early experiments were not always grand in scale, but they were significant in cultivating a disciplined approach to scientific investigation. He conducted studies in optics, exploring the nature of light and color, using prisms to observe the splitting of sunlight. Although these experiments were rudimentary compared to his later work, they demonstrate a mind attuned to careful observation and systematic testing. He did not accept appearances at face value. He sought to measure, quantify, and understand the mechanisms underlying observable phenomena. Even as a young man, Newton exhibited the patience and precision that would characterize decades of research, working tirelessly to uncover the patterns that others overlooked. Another critical aspect of Newton's formative years was his intense focus on solitary study. While many young men of his age might have been absorbed in social life or local affairs, Newton often preferred the quiet of his room or the countryside, immersed in books and experiments. This solitary inclination was both a strength and a challenge. It allowed him the concentration necessary to develop original ideas, yet it sometimes isolated him from mentors and peers who could have provided guidance or collaboration. Nevertheless, Newton's preference for solitude nurtured a self-reliance and internal rigor that would become central to his scientific method. He learned to question everything, to test hypotheses rigorously, and to rely on reason and evidence rather than authority or tradition. Newton's formative environment, both in terms of his family circumstances and the physical landscape of Lincolnshire, played a subtle but crucial role in shaping his curiosity. The rolling fields, orchards, streams, and night skies of Woolsthorpe offered a living laboratory for observation. He could watch an apple fall, track the motion of water in a stream, or study the phases of the moon with meticulous attention. The quiet rural environment provided both space and time for thought, free from the distractions and rigid hierarchies of city life. Newton learned to observe patterns, connect causes and effects, and formulate questions that probe the deepest principles of nature. In these simple acts of watching and thinking, the foundations of his revolutionary ideas were laid. The young Newton's temperament also contributed to his early intellectual development. He was known for his intense curiosity, his love of puzzles, and his refusal to accept easy explanations. This intellectual restlessness meant that he was constantly seeking more challenging problems, more profound insights, and more precise formulations. He would spend hours contemplating questions about motion, light, and mathematics, sometimes neglecting his physical comfort or social obligations in the process. This intense focus, combined with a remarkable memory and capacity for logical reasoning, allowed him to assimilate vast amounts of knowledge and identify gaps where new understanding was required. In many ways, Newton's early life exemplifies the combination of innate talent and relentless discipline that defines extraordinary genius. Mentorship and informal guidance also played a role in Newton's early growth. While his family could not provide a scholarly environment, certain local teachers and scholars recognized his exceptional abilities and encouraged him to pursue his studies. They provided access to books, instruments, and ideas that expanded his horizons. Through these interactions, Newton learned not only facts and techniques, but also the habits of critical thinking and rigorous inquiry. He absorbed lessons about observation, deduction, and systematic experimentation, skills that would become central to his later scientific achievements. Even without formal instruction at the highest levels, Newton's early encounters with mentorship laid important groundwork for the intellectual independence that would define his career. As Newton approached adulthood, his intellectual curiosity became increasingly ambitious. He began contemplating not just isolated problems, but the underlying principles that governed all natural phenomena. The questions that occupied his mind were profound. Why do objects fall? How do celestial bodies move? What is the nature of light? How can we describe motion mathematically? These were not questions with ready answers, yet Newton pursued them with a combination of practical observation, imaginative reasoning, and mathematical analysis. He was laying the mental foundations for discoveries that would eventually unify the laws of motion, the principles of calculus, and the understanding of gravitation. The context of 17th century England also influenced Newton's intellectual development. He grew up in a time of social, political, and scientific transformation. The scientific revolution was reshaping the understanding of the natural world, challenging traditional Aristotelian and religious explanations. Figures like Galileo, Descartes, and Kepler were introducing methods based on observation, experimentation, and mathematics. Newton absorbed these ideas indirectly through books and correspondence, building upon them while moving beyond their limitations. His early life demonstrates how a brilliant mind, even in relative isolation, can integrate existing knowledge, identify its shortcomings, and push toward novel insights. Newton's early life also reveals the interplay between personal adversity and intellectual growth. The loss of his father, the partial absence of his mother, and periods of social isolation could have been limiting factors, yet they fostered a resilience, independence, and capacity for self-directed study. Newton learned to rely on his own judgment, to test ideas rigorously, and to persist in the face of difficulty or uncertainty. These traits would prove essential when he later tackled problems that had stymied the greatest minds of his time. His formative years, marked by both challenge and opportunity, cultivated the qualities of perseverance, meticulousness, and intellectual courage that became hallmarks of his life's work. Another remarkable aspect of Newton's early development was his capacity for synthesizing diverse fields of knowledge. He was not content to study mathematics in isolation or merely to observe nature without explanation. Instead, he sought connections between numbers and geometry, between motion on Earth and the movement of the stars, between light and color. This ability to integrate insights across domains would later allow him to formulate groundbreaking theories that unified seemingly disparate phenomena. In his early years, this integrative thinking began to emerge, showing a mind capable of extraordinary abstraction and creativity. As he neared the age of formal higher education, Newton had already amassed a rich foundation of observation, experimentation, and mathematical skill. Though his achievements at this stage may seem modest compared to his later monumental discoveries, they were the indispensable first steps in the formation of a scientific genius. The curiosity, discipline, and intellectual independence cultivated during these formative years allowed him to enter Cambridge not merely as a student, but as a thinker poised to challenge established knowledge and expand the boundaries of human understanding. His early life demonstrates that genius is not only a product of innate talent, but also of careful cultivation, persistent inquiry, and the ability to see patterns and principles where others see only complexity or disorder. In reflecting on this period, one recognizes that Newton's childhood and adolescence were not marked by extraordinary privilege, formal mentorship at the highest levels, or access to great institutions. Instead, they were defined by curiosity, resilience, and an insatiable desire to understand the world. Through observation, experimentation, and reflection, he built an intellectual framework that would support his later revolutionary contributions to science. His early life teaches us the importance of nurturing curiosity, valuing patience and careful study, and cultivating the discipline to pursue questions that may have no immediate answers, but whose pursuit transforms both the seeker and the world. It is remarkable that from the quiet village of Woolsthorpe, amidst the ordinary rhythms of rural life, emerged a mind capable of grasping the most extraordinary truths about the universe. Newton's early years remind us that genius is often the product of an unrelenting curiosity, a willingness to observe closely, and a relentless drive to understand the causes behind phenomena. These formative experiences, combining intellectual, emotional, and environmental factors, laid the foundation for a life that would forever change how humanity perceives the cosmos. In studying his early life, we gain insight not only into the mind of Isaac Newton, but also into the conditions that cultivate profound scientific discovery, a combination of innate talent, disciplined practice, and an enduring curiosity about the natural world. Isaac Newton's journey into mathematics marked a transformative phase of his life, a period when his insatiable curiosity evolved into the formal structures of reasoning that would underpin much of modern science. From his earliest experiments with numbers and geometric patterns, Newton's mind demonstrated a remarkable capacity for abstraction, analysis, and synthesis. By the time he entered Cambridge University, he had already laid the groundwork for a mathematical vision that would revolutionize not only physics, but also the way humanity conceptualizes change, motion, and the relationships between quantities. Mathematics, for Newton, was more than a collection of tools. It was a language capable of expressing the very laws of nature, providing a bridge between observation and understanding. Newton's early exposure to mathematical concepts was primarily through classical works, including those of Euclid, whose elements introduced him to rigorous logic, deductive reasoning, and geometric principles. Euclid's treatment of shapes, proportions, and proofs fascinated Newton, who recognized the potential of mathematics as a precise method to investigate the world. Beyond the basic geometry taught in his grammar school, Newton delved into the subtleties of ratios, infinitesimal magnitudes, and the behavior of curves, gradually moving toward more advanced concepts that would eventually form the foundation for calculus. His early engagement with mathematics was characterized by both discipline and creativity. He absorbed established knowledge while simultaneously exploring questions that had not yet been addressed by scholars of his time. The historical context of mathematical discovery in Newton's era played a crucial role in shaping his development. The 17th century was a period of intellectual ferment, with new ideas about mathematics, astronomy, and physics circulating widely across Europe. The work of René Descartes introduced analytic geometry, linking algebraic equations to geometric curves and providing a powerful framework for visualizing relationships between quantities. Similarly, the studies of Pierre de Fermat on maxima, minima, and tangents to curves hinted at the possibilities of systematically describing motion and change. Newton absorbed these influences, recognizing that a more comprehensive mathematical system could unify these fragmented insights, providing a universal language to describe the dynamics of natural world. It was within this intellectual environment that Newton began developing the foundations of what would later become his theory of calculus. Known to him as the method of fluxions, this new branch of mathematics aimed to describe how quantities change over time. Newton understood that the universe was in constant motion, planets orbiting the sun, projectiles tracing arcs, and rivers flowing to the sea, and that these processes could be understood through precise quantitative relationships. Traditional algebra and geometry were insufficient for capturing continuous motion, rates of change, or the accumulation of quantities over time. Newton's insight was to conceive of mathematical tools capable of dealing with the infinitely small and the infinitely large, thereby allowing precise calculation of areas, slopes, velocities, Accelerations. Newton's approach to calculus was deeply rooted in his broader philosophy of science. He believed that nature operated according to simple, universal laws, and that these laws could be expressed mathematically. Observing the motion of objects both on Earth and in the heavens, he sought methods to quantify acceleration, momentum, and forces. This required a novel approach, as conventional mathematics lacked the means to describe instantaneous change. Through intense thought, experimentation with problems, and rigorous logical reasoning, Newton devised the concepts of fluxions and fluence, the changing quantities and their rates of change, which would allow him to calculate motion in a precise and general way. In essence, he created a mathematical mirror of reality, capable of reflecting the continuous flow of the universe in symbolic form. The process of developing calculus was not instantaneous. Years of the citerates that estad, experimentation, and reflection. Newton's retreat from Cambridge during the plague years of 1665 proved particularly fruitful. Isolated at Woolsthorpe Manor, he devoted himself entirely to study, free from the obligations of formal academic life. During this period, he conducted experiments with light, motion, and gravity, but he also made significant strides in mathematics. He developed methods for finding tangents to curves, calculating areas under curves, and analyzing the rates at which quantities change, all fundamental aspects of calculus. These achievements were not the result of mere memorization or replication of existing knowledge. They were the product of original thought, a combination of imagination, logical precision, and intimate engagement with the problems posed by nature. One of the most striking aspects of Newton's mathematical development was the interconnection between his abstract reasoning and his observations of the physical world. For example, in contemplating the motion of a falling apple or the trajectory of a planet, Newton recognized that understanding acceleration required a new mathematical approach. The traditional methods of geometry could describe positions or distances, but could not capture the continuous variation of speed or force over time. Through his concept of fluxions, Newton created a tool that allowed him to calculate instantaneous velocity, acceleration, and the cumulative effect of forces. In doing so, he not only advanced mathematics, but also provided the instruments necessary to formulate the laws of motion and universal gravitation, which would later revolutionize physics. The conceptual elegance of Newton's calculus also reflected his broader intellectual vision. He sought simplicity and generality, aiming to describe complex phenomena through fundamental principles. Rather than treating each physical situation as a separate problem, he recognized that a unified mathematical framework could explain a vast array of natural processes. This insight demonstrated his exceptional ability to abstract general laws from specific observations, a hallmark of scientific genius. Newton's work in calculus was not merely a technical achievement. It was a philosophical statement about the coherence and intelligibility of the universe, revealing that even the most intricate and dynamic processes could be understood through reason and precise calculation. Newton's approach to mathematics was also profoundly experimental in spirit, though conducted primarily in the mind rather than the laboratory. He tested his methods on a variety of problems, exploring their implications and refining their precision. He examined the curvature of curves, the summation of infinite series, and the behavior of forces in motion. Each new problem served as both a test and an extension of his mathematical framework, reinforcing the connection between abstract reasoning and empirical reality. In this way, Newton's calculus became not only a set of symbolic tools, but a dynamic instrument for probing the natural world, enabling predictions that could be verified through observation. It is important to note that Newton's development of calculus occurred independently of other contemporary mathematicians, most notably Gottfried Wilhelm Leibniz. While both men arrived at similar conclusions about the mathematics of change, their approaches and notations differed. Newton's method of fluxions emphasized the dynamic process of motion, focusing on quantities as they flow and change, whereas Leibniz's differential notation provided a more symbolic and formalized approach. The eventual priority dispute between Newton and Leibniz underscores the revolutionary nature of the discovery, highlighting that multiple minds were converging on the same fundamental insights into the mathematics of change. Newton's approach, however, was deeply intertwined with his understanding of physical reality, demonstrating his ability to merge abstract reasoning with empirical observation. The implications of Newton's mathematical innovations were profound and far-reaching. By creating a systematic method to describe change, he provided tools that could be applied across a vast range of scientific and engineering problems. Calculus allowed for the precise prediction of motion, the calculation of areas and volumes, the modeling of natural phenomena, and the formulation of physical laws with unparalleled accuracy. It laid the groundwork not only for Newton's own discoveries in mechanics, optics, and astronomy, but also for the subsequent development of physics, engineering, and technology. The ability to understand and manipulate the mathematics of continuous change transformed human capability, providing a means to bridge abstract theory and practical application in unprecedented ways. Newton's work in mathematics also illustrates the interplay between creativity and discipline in scientific achievement. Developing calculus required not only inspiration and imagination, but also rigorous logical reasoning, meticulous attention to detail, and persistent effort over years. Newton would often immerse himself in problems for extended periods, working in isolation, and testing every step of his reasoning to ensure accuracy and consistency. His notebooks reveal an extraordinary level of diligence, with carefully written calculations, corrections, and refinements. This combination of intellectual vision and methodical rigor allowed him to construct a coherent and powerful mathematical framework, capable of supporting the most ambitious inquiries into the laws of nature. Another remarkable aspect of Newton's mathematical development was his ability to foresee its broader applications. While initially driven by problems in geometry and motion, he recognized that calculus could be used to describe a wide range of phenomena, from planetary orbits to the behavior of fluids, from the dynamics of pendulums to the properties of light. The methods he developed offered a universal toolkit for analysis. This visionary quality demonstrates Newton's ability to think beyond immediate problems, anticipating the future utility of his discoveries. His mathematics was not merely a solution to specific questions. It was a framework for understanding the universe itself. Newton's engagement with mathematics during this period also exemplifies the integration of intuition and formal reasoning. While he relied on rigorous logical procedures, he also trusted his ability to envision relationships and patterns in the natural world. This balance between imaginative insight and disciplined calculation allowed him to explore problems that others might have dismissed as intractable. He could see the behavior of quantities in motion, conceptualize infinitesimal changes, and translate these insights into precise symbolic form. The development of calculus, thus, reflects both the creativity and the analytical power of Newton's mind, showcasing the dual aspects of genius that enable transformative discoveries. As Newton matured into a fully realized mathematician, the impact of his work began to extend beyond personal exploration. His mathematical methods provided the foundation for his formulation of the laws of motion, his theory of gravitation, and his studies in optics. Calculus became the essential tool that allowed him to unify terrestrial and celestial mechanics, to predict planetary orbits, and to describe the dynamics of bodies under force. Without this mathematical framework, his subsequent achievements would have been impossible. Calculus was not an isolated triumph of abstraction. It was the key that unlocked a deeper understanding of the physical universe, demonstrating the inseparability of mathematics and science in Newton's thought. The development of calculus also highlights Newton's philosophical outlook. He approached mathematics as a way of revealing the inherent order and simplicity of the universe. Every problem he encountered, whether in motion, geometry, or optics, was an opportunity to uncover the underlying principles that governed natural phenomena. In creating a language capable of describing continuous change, Newton was asserting that the universe could be understood, predicted, and explained through reason. This perspective reflects the broader intellectual ethos of the scientific revolution, emphasizing observation, experimentation, and mathematical description as the pathways to knowledge. Newton's calculus, in this sense, was both a technical innovation and a philosophical statement about the intelligibility of the cosmos. As Isaac Newton continued to refine his mathematical thinking, the methods he developed became increasingly sophisticated, allowing him to tackle problems that had long eluded other scholars. The notion of fluxions and fluents, central to his approach to calculus, enabled him to conceptualize quantities not as static entities, but as dynamically changing over time. This conceptual leap was revolutionary. Before Newton, most mathematics dealt with fixed quantities, lengths, areas, and volumes, but had no formal way to describe how these quantities changed instantaneously. By introducing the idea of fluxions, Newton created a framework for understanding the motion of numbers themselves, providing the tools necessary to analyze velocity, acceleration, and the cumulative effects of continuous change. Newton's method of fluxions was deeply intertwined with his study of physical phenomena. For instance, in analyzing the trajectory of a projectile, he could use fluxions to calculate how velocity changed at each moment along the curve of flight. By connecting the changing position of an object to the forces acting upon it, he was able to derive equations that accurately described motion. This approach demonstrated a remarkable integration of mathematics and physical intuition. Newton's calculations were not mere abstract exercises, but were directly grounded in the behavior of the natural world. Each fluxion represented a tangible aspect of motion, linking mathematical symbols to empirical reality in a way that no previous scholar had accomplished. Another critical aspect of Newton's work during this period was his exploration of infinite series. He recognized that complex curves and functions could be expressed as sums of infinitely many terms, allowing for precise approximations and solutions to problems that were otherwise intractable. This insight was crucial for analyzing nonlinear motion, calculating areas under irregular curves, and predicting the behavior of complex systems. Newton's mastery of infinite series illustrates not only his technical skill, but also his intellectual daring. He was willing to engage with concepts that challenged conventional mathematical wisdom, extending the boundaries of what could be expressed and calculated with precision. Newton's mathematical creativity was also evident in his work on quadratures, the determination of areas under curves. This problem, which had occupied mathematicians for centuries, was transformed by Newton's calculus into a systematic procedure. Using his method of fluxions, he could relate the rate of change of a quantity to the accumulation of that quantity over time, effectively providing a universal solution to the problem of integration. This achievement demonstrates Newton's ability to synthesize abstract reasoning with practical problem solving, showing that mathematics could serve as both a language of description and a tool of computation. The elegance of his methods lay in their generality. A single framework could handle a wide variety of problems, from the motion of planets to the flow of water in a stream. During this period, Newton also explored the application of calculus to curves and geometric problems. He examined tangents, normals, and curvature, developing techniques that allowed him to describe the instantaneous slope and bending of curves in precise terms. These methods were not only mathematically innovative, but also directly relevant to understanding motion and forces. For example, determining the tangent to a curve was equivalent to calculating the instantaneous velocity of a moving object, linking geometry directly to the dynamics of physical systems. Newton's ability to see these connections reflects a profound insight. Mathematics was not an isolated discipline, but a lens through which the patterns of the universe could be perceived and quantified. The development of calculus also had a profound impact on Newton's subsequent work in physics. With these tools at his disposal, he could formalize the laws of motion, describe planetary orbits, and calculate the effects of gravitational forces. Without calculus, it would have been nearly impossible to express these principles in a precise, predictive form. Calculus allowed Newton to move beyond qualitative descriptions of nature and into a realm of quantitative precision, where predictions could be tested against observation. This shift from descriptive to predictive science marked a turning point in human understanding, laying the foundation for modern physics and engineering. Newton's process of developing calculus was characterized by intense solitude, introspection, and meticulous attention to detail. During the years of the plague, when Cambridge University was closed, he retreated to Woolsthorpe Manor and devoted himself to rigorous study. Isolated from colleagues and formal instruction, he worked through problems at his own pace, testing methods, refining notation, and ensuring logical consistency. His notebooks from this period reveal a mind deeply engaged in exploration, recording calculations, diagrams, and reflections in painstaking detail. This disciplined approach was essential for managing the complexity of the problems he tackled, allowing him to build a coherent and comprehensive mathematical framework from first principles. One of the remarkable aspects of Newton's development of calculus was his ability to anticipate its broader applications. While initially motivated by problems in geometry and motion, he recognized that the principles he had developed could be applied to virtually any domain involving continuous change. From the mechanics of celestial bodies to the flow of fluids, from the analysis of vibrations to the study of light, the methods of fluxions and integration provided a universal toolkit for exploration. Newton's foresight in this regard demonstrates both the depth of his understanding and his visionary capacity to see the potential of his discoveries beyond their immediate context. Newton's contemporaries soon began to recognize the revolutionary nature of his work, though he was often cautious about publication. The delay in disseminating his methods led to the famous dispute with Gottfried Wilhelm Leibniz over the invention of calculus. While both men developed similar mathematical concepts independently, their approaches and notations differed. Newton's fluxions emphasized the dynamic aspect of changing quantities, whereas Leibniz's differential notation provided a more symbolic and formalized structure. The controversy highlights not only the originality of Newton's thought, but also the intense intellectual ferment of the period, in which multiple minds were converging on fundamental truths about the mathematics of change. Despite the dispute, the essential contribution of Newton's methods remained undeniable, shaping the course of science for centuries to come. The philosophical implications of Newton's calculus were as profound as the technical achievements. By creating a systematic method for describing change, Newton implicitly asserted that the universe itself was orderly, predictable, and intelligible. Fluxions allowed him to describe not just static objects, but the flow of motion, the accumulation of forces, and the dynamics of the natural world. This approach reflects a deeply rational view of the cosmos, that underlying apparent complexity were simple, universal principles capable of precise mathematical expression. Newton's mathematics thus became a bridge between abstract reasoning and empirical observation, embodying the spirit of the scientific revolution and the Enlightenment ideals of rationality and order. Another dimension of Newton's mathematical development was the interplay between theory and experimentation. While much of his work on calculus was conducted as abstract reasoning, he continually tested his methods against observable phenomena. Problems in motion, planetary orbits, and optics provided concrete challenges that guided his refinement of techniques. This feedback loop between theory and empirical evidence ensured that Newton's mathematics was not merely formal manipulation, but a powerful tool for understanding reality. The integration of calculation, observation, and logical deduction exemplifies Newton's broader methodological approach, which would define his scientific achievements in every field he touched. Newton's work also exemplified the importance of perseverance and intellectual courage. Developing a system as revolutionary as calculus required him to think in ways that were unfamiliar, counterintuitive, and often controversial. He had to grapple with concepts of the infinitely small, instantaneous change and continuous motion, ideas that challenged conventional mathematical wisdom. Many of his contemporaries were reluctant to engage with such abstract and demanding problems. Yet Newton's determination, combined with his ability to visualize and manipulate complex quantities mentally, allowed him to overcome these challenges, producing a body of work that was both rigorous and profoundly original. The long-term impact of Newton's calculus cannot be overstated. It provided the foundation for his later discoveries in mechanics, gravitation, and optics, enabling him to formulate laws that could predict planetary motion, describe falling bodies, and explain the behavior of light. Beyond Newton's own work, calculus became a central tool for countless generations of scientists, engineers, and mathematicians. Its applications range from designing bridges and calculating trajectories to modeling population, dynamics, and analyzing electrical circuits. In every case, the methods that Newton developed during his formative mathematical years continue to shape human understanding and technological progress. Newton's mastery of mathematics also reflects a broader lesson about the development of scientific genius. His achievements were not the product of innate talent alone. They were the result of disciplined study, persistent experimentation, and the integration of abstract reasoning with empirical observation. The creation of calculus required not only insight, but also meticulous attention to detail, careful testing, and a willingness to engage with difficult and unfamiliar concepts. Newton's early mathematical development illustrates how curiosity, imagination, and intellectual rigor combine to produce discoveries that transform human knowledge and capability. As he continued to refine his methods, Newton demonstrated an extraordinary ability to synthesize ideas across disciplines. His mathematical innovations were not isolated abstractions, but tools for understanding the physical universe. By linking fluxions to motion, by using infinite series to approximate complex curves, and by integrating geometric intuition with algebraic formalism, he created a comprehensive system analyzing the dynamics of nature. This integrative approach allowed him to tackle problems that had stymied generations of scholars, demonstrating that mathematics could serve both as a descriptive and predictive science. Newton's development of calculus, thus, represents a pinnacle of intellectual achievement, combining creativity, rigor, and a profound understanding of the natural world. Isaac Newton's formulation of the laws of motion represents one of the most profound contributions to human understanding, fundamentally changing how we perceive the universe. Before Newton, scholars had long debated the principles that govern movement. Aristotle, for instance, had suggested that objects moved only when acted upon by an external force, and that motion naturally ceased in the absence of such a force. While this intuitive view may have aligned with everyday experience, it failed to account for the more complex dynamics of celestial bodies, projectiles, and falling objects. Newton, through careful observation, experimentation, and mathematical reasoning, resolved these inconsistencies by formulating laws that could universally describe both terrestrial and celestial motion. The essence of Newton's achievement lies in the recognition that the same principles govern objects on Earth and in the heavens. Whereas earlier thinkers treated terrestrial physics and celestial mechanics as fundamentally different realms, Newton unified them under a single framework. This insight was revolutionary. He demonstrated that the motion of a falling apple, the swing of a pendulum, and the orbit of the moon around Earth could all be understood through the same mathematical laws. By establishing this unification, Newton provided a coherent, predictive framework for the entire physical universe, effectively bridging a gap that had persisted for centuries. Newton's first law, often called the law of inertia, asserts that an object at rest remains at rest, and an object in motion continues in uniform motion unless acted upon by an external force. This principle challenged prevailing assumptions, emphasizing that motion is not the natural consequence of force, but rather a state that persists until a force intervenes. The law of inertia provided a foundation for understanding both terrestrial phenomena, such as the sliding of a block or the flight of a projectile, and celestial motion, where planets maintain their orbits absent significant external interference. By conceptualizing motion in this way, Newton introduced a level of abstraction that allowed for general, universal descriptions of physical behavior. The second law of motion, which relates force, mass, and acceleration, provided the mathematical foundation for predicting how objects respond to forces. Expressed succinctly as F equals ma, this law allows for the calculation of the acceleration an object experiences when subjected to a specific force. It formalized the connection between cause and effect in physical systems, transforming qualitative observations into quantitative predictions. This principle is remarkable not only for its clarity, but for its universality. It applies equally to a rolling cart, a cannonball in flight, or a planet moving through space. Through the second law, Newton gave scientists and engineers a powerful tool to analyze and predict outcomes with precision, enabling advances that continue to shape technology and industry today. Newton's third law, often summarized as for every action, there is an equal and opposite reaction, provided insight into the interactions between bodies. This principle explains phenomena ranging from the recoil of a gun to the propulsion of a rocket and the gravitational pull between celestial bodies. It emphasizes that forces do not exist in isolation, but always arise from interactions, a concept that revealed the deep symmetry in nature's behavior. By articulating this law, Newton provided a fundamental principle that governs dynamics at every scale, from microscopic collisions to the movements of stars and planets. These three laws, taken together, created a comprehensive framework for understanding motion in both earthly and cosmic contexts. Newton's genius was not merely in formulating these principles, but in recognizing their universal applicability. He demonstrated that the same mathematical relationships that govern a falling apple also dictate the motion of the moon, the planets, and even comets. This unification represented a paradigm shift in science, replacing fragmented and often contradictory explanations with a coherent, predictive, and mathematically grounded model of the physical universe. Central to this unification was Newton's work on universal gravitation. Observing the apparent similarity between the motion of falling objects and celestial orbits, he hypothesized that every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. This law explained not only terrestrial phenomena, such as the falling of apples or the behavior of tides, but also the precise elliptical orbits of planets described earlier by Johannes Kepler. By applying his laws of motion to gravitational attraction, Newton could predict the motions of heavenly bodies with extraordinary accuracy, demonstrating that the heavens and earth were governed by the same principles, a radical departure from centuries of thought. Newton's approach combined observation, experimentation, and mathematics in a way that had never been done before. He did not rely on philosophical speculation or authority, but tested his hypotheses against empirical evidence and expressed them in precise mathematical terms. For example, by analyzing the motion of planets using his laws, he could derive Kepler's empirical laws of planetary motion from first principles, providing a theoretical foundation that explained why the planets moved as they did. This ability to unify theory and observation through mathematics marked a turning point in scientific methodology and established Newton as a towering figure in the history of science. The impact of Newton's laws extended beyond physics into broader human understanding. By demonstrating that natural phenomena could be described by universal, predictable laws, he provided a model for systematic investigation and rational inquiry. His work inspired future generations of scientists, from engineers designing bridges and machines to astronomers calculating planetary trajectories. The laws of motion and universal gravitation became fundamental tools for exploring the natural world, enabling discoveries ranging from the behavior of fluids and gases to the motion of celestial bodies across vast distances. Moreover, Newton's unification of terrestrial and celestial mechanics symbolized a deeper intellectual achievement, the recognition of order and regularity in the universe. Where previously the heavens were seen as mysterious and governed by different principles from Earth, Newton revealed a cosmos governed by consistent, discoverable laws. This vision fundamentally altered humanity's conception of its place in the universe, showing that natural phenomena, no matter how complex or distant, could be understood through reason, observation, and mathematics. Newton's laws thus represent not only technical brilliance, but also a philosophical shift toward a rational, comprehensible cosmos. In practical terms, Newton's laws laid the groundwork for countless applications in science and technology. Engineers use these principles to design machines, vehicles, and structures that function predictably and safely. Astronomers employ them to calculate orbital trajectories, plan space missions, and understand the dynamics of galaxies. Even in everyday life, from sports to transportation, the behavior of objects can be analyzed and predicted using Newtonian mechanics. The universality and precision of these laws make them enduring tools for both theoretical exploration and practical problem solving. In conclusion, Newton's laws of motion and his unification of celestial and terrestrial mechanics represent a cornerstone of scientific thought. By formulating principles that apply universally, expressing them mathematically, and grounding them in observation, he transformed humanity's understanding of the natural world. The laws of motion provide clarity and predictability in a previously mysterious universe, while the concept of universal gravitation bridges the gap between Earth and the cosmos. Newton's insights demonstrate the power of combining observation, experimentation, and mathematical reasoning to uncover fundamental truths. They remind us that the universe, no matter how vast or complex, can be understood through careful study, logical analysis, and the persistent pursuit of knowledge, a legacy that continues to guide science and inspire wonder centuries after his time. Isaac Newton's formulation of the law of universal gravitation stands as one of the most profound achievements in the history of science, fundamentally transforming humanity's understanding of cosmos. Before Newton, the motion of celestial bodies and the falling of objects on Earth were seen as largely separate phenomena. Scholars such as Aristotle and Ptolemy treated the heavens as governed by a different set of principles from those on Earth, attributing celestial motion to divine or perfect mechanisms and terrestrial motion to ordinary, often chaotic forces. Even Copernicus and Kepler, who revolutionized astronomy with heliocentric models and elliptical orbits, primarily relied on empirical observation to describe planetary motion rather than uncovering the underlying forces that governed it. Newton's genius was in recognizing a universal law that could simultaneously explain both terrestrial and celestial phenomena, revealing a universe bound together by predictable mathematical principles. At the heart of Newton's insight was the realization that gravity was not a localized or isolated force, but a universal one. He proposed that every particle of matter in the universe attracts every other particle with a force proportional to their masses, and inversely proportional to the square of the distance between them. This simple yet profound statement, the law of universal gravitation, provided a framework that could account for phenomena ranging from the falling of an apple to the orbiting of planets and moons. The elegance of this law lay not only in its simplicity, but also in its universality. A single principle could describe an immense range of behaviors, uniting the motions of Earth-bound objects with those of celestial bodies across the vastness of space. Newton's law of gravitation emerged from a combination of observation, mathematical reasoning, and careful thought experiments. According to popular legend, he was inspired by the fall of an apple, which led him to question why objects always fall straight toward the Earth, and whether the same force might extend to the moon and beyond. While the anecdote has been romanticized, it reflects the essence of Newton's approach: careful attention to everyday phenomena combined with imaginative reasoning about their broader implications. By considering how a force acting at a distance could govern both falling objects and orbital motion, Newton began to formulate a unifying principle that bridged the gap between Earth and the heavens. A critical element of Newton's law is the mathematical relationship between force, mass, and distance. The gravitational force between two objects increases with their masses and decreases with the square of the distance separating them. This inverse, square relationship explains why gravity diminishes with distance yet never truly disappears, allowing the same force that causes an apple to fall to govern the motion of planets millions of miles away. By combining this principle with his laws of motion, Newton was able to calculate orbital trajectories with unprecedented accuracy, deriving the elliptical paths of planets from first principles, rather than relying solely on observation. This ability to predict motion quantitatively marked a revolutionary shift in the study of the cosmos. Newton's law of universal gravitation also provided a theoretical foundation for previously observed but unexplained phenomena. For instance, the tides, long associated with the Moon, could now be understood in terms of the gravitational pull exerted by both the Moon and the Sun. Similarly, the precession of planetary orbits and the perturbations of cometary paths could be analyzed mathematically using the same principles. By providing a single explanatory framework, Newton transformed disparate observations into a coherent, predictive model. This not only deepened scientific understanding, but also demonstrated the power of mathematics to reveal the hidden order of the universe. The implications of Newton's gravitational theory were far-reaching and transformative. By showing that the same force governs both terrestrial and celestial bodies, Newton fundamentally altered humanity's conception of the cosmos. No longer were the heavens mysterious or separate. They operated according to the same laws as Earth. This unification reinforced the notion that the universe is intelligible, predictable, and governed by principles that can be discovered through observation, experimentation, and reasoning. It represented a philosophical as well as scientific breakthrough, replacing superstition and speculation with a framework of rational inquiry. Newton's law also laid the groundwork for modern astronomy and space exploration. By providing the tools to calculate planetary positions and trajectories, it enabled astronomers to predict celestial events, such as eclipses and transits, with remarkable accuracy. The same principles guide the motion of satellites, spacecraft, and interplanetary probes today. Newton's insight transformed humanity's ability to navigate and understand the cosmos, bridging the gap between theoretical understanding and practical application. Without this foundation, space exploration, as we know it, would have been impossible. Another remarkable aspect of Newton's gravitational theory is its methodological significance. Newton did not merely propose a speculative idea. He rigorously tested it against observation and integrated it with a comprehensive mathematical framework. By combining the law of gravitation with his laws of motion, he could derive Kepler's laws of planetary motion, demonstrating that the empirical rules observed by astronomers were consequences of universal physical law. This approach exemplifies the power of synthesizing empirical evidence with theoretical reasoning, a method that remains central to scientific inquiry today. Newton's work illustrates how observation, mathematics, and logical reasoning can converge to reveal fundamental truths about the universe. Newton's law of universal gravitation also exemplifies the elegance and simplicity that often characterizes profound scientific insights. Despite its simplicity, the law provides predictive power across scales, from apples falling in orchards to the motion of planets, moons, and comets. It unifies diverse phenomena under a single principle, demonstrating that the complexity of the cosmos can arise from simple, consistent rules. This realization transformed the study of nature, showing that even the most intricate behaviors could be understood and predicted through careful analysis. The discovery of universal gravitation also influenced subsequent scientific thought and philosophy. It reinforced the idea that the universe operates according to consistent, discoverable laws, a principle that inspired future generations of scientists and thinkers. Figures such as Laplace, Lagrange, and Einstein built upon Newtonian mechanics to advance celestial mechanics, dynamical systems, and the theory of relativity. While later developments would refine and expand upon Newton's insights, the core principle of universal gravitation remained a foundation for understanding the structure and dynamics of the universe. Newton's achievement in formulating universal gravitation underscores the interplay between observation, imagination, and mathematical reasoning. He observed everyday phenomena, imagined the forces that could explain them, and expressed these ideas through precise mathematics. This integration of empirical insight with abstract reasoning exemplifies the scientific method and highlights the depth of Newton's intellectual vision. He did not merely describe phenomena. He sought to uncover the underlying causes, demonstrating that the universe operates according to intelligible, universal laws. In conclusion, Newton's law of universal gravitation represents a monumental step in humanity's understanding of the cosmos. By revealing that the same force governs both terrestrial and celestial bodies, Newton unified previously separate domains of knowledge, providing a coherent framework for explaining motion, predicting planetary orbits, and understanding the forces that shape the universe. The law's elegance, universality, and predictive power exemplify the transformative impact of rigorous observation, imaginative reasoning, and mathematical analysis. Newton's gravitational theory not only advanced science, but also reshaped humanity's perception of the cosmos, demonstrating that the universe, in all its vastness and complexity, operates according to discoverable and intelligible principles. This achievement stands as a testament to the power of the human mind to comprehend the natural world and to reveal the hidden order that governs it, inspiring generations of scientists and thinkers to explore the cosmos with curiosity, precision, and wonder. Isaac Newton's contributions to optics stand as a testament to his ingenuity and experimental rigor, revealing the fundamental nature of light and color and establishing principles that would shape physics for centuries. While Newton is often celebrated for his laws of motion and universal gravitation, his work in optics demonstrates a complementary aspect of his genius, a meticulous combination of observation, experimentation, and theoretical reasoning. His studies in this field not only resolved long-standing debates about the nature of light, but also exemplified the scientific method, highlighting the interplay between empirical evidence and mathematical explanation. Before Newton, the nature of light was poorly understood, and scholars held competing theories. One prevailing view, advocated by Descartes, suggested that light was a pressure or disturbance transmitted instantaneously through a medium, somewhat like sound. Another theory, rooted in the Aristotelian tradition, regarded light as a property of the medium through which it traveled, lacking independent existence. Color, similarly, was often thought to arise from modifications of white light by reflection or refraction, rather than being an intrinsic property of light itself. These divergent ideas reflected both the observational limitations of the time and the absence of rigorous experimental techniques capable of testing the behavior of light quantitatively. Newton approached these questions with characteristic precision and innovation. Using simple yet ingenious experiments involving prisms, he demonstrated that white light is not homogeneous but composed of a spectrum of colors. By passing sunlight through a prism, he observed that it split into distinct colors, red, orange, yellow, green, blue, indigo, and violet, forming a continuous spectrum. He further showed that these colors could be recombined using a second prism to reproduce white light, conclusively demonstrating that color is not produced by the prism or medium, but is a fundamental property of light itself. This experiment not only resolved centuries of speculation, but also exemplified Newton's approach to science: careful observation, controlled experimentation, and logical deduction leading to generalizable conclusions. One of the revolutionary aspects of Newton's work in optics was his emphasis on quantification and reproducibility. He did not rely solely on qualitative description, but meticulously measured angles, distances, and intensities, ensuring that his conclusions could be tested and verified. For instance, he carefully studied the refraction of light at different angles and its dispersion through various materials, laying the groundwork for understanding the precise behavior of light rays. By introducing such rigor into the study of optics, Newton helped transform it from a largely speculative discipline into a systematic, empirical science capable of predictive power. Newton also extended his studies to the phenomenon of diffraction and the behavior of light as it passes through lenses and apertures. While some of these questions remained only partially understood in his lifetime, he recognized that light exhibited complex interactions with matter, including bending, spreading, and interference. He explored the limitations of optical instruments, investigating chromatic aberration in lenses, and devised techniques to minimize distortion in telescopes. These investigations not only improved practical tools for observation, but also provided deeper insight into the properties of light, influencing the design of optical instruments for generations. Another crucial contribution of Newton's optical research was his development of the corpuscular theory of light, which proposed that light is composed of small particles, or corpuscles, that travel in straight lines. This theory contrasted with the wave theory advocated by contemporaries such as Christian Huygens. Newton's particle model explained phenomena such as reflection and refraction with remarkable clarity, and provided a coherent framework for analyzing the behavior of light in various media. While later developments would reveal that light exhibits both particle-like and wave-like properties, Newton's corpuscular theory represented a decisive step toward a systematic understanding of optical phenomena and exemplified the power of theoretical reasoning grounded in empirical observation. The prism experiments also had broader scientific implications. By revealing that white light is composed of different colors, Newton showed that the apparent properties of natural phenomena could often be decomposed into simpler, fundamental components. This approach, breaking complex phenomena into constituent elements to understand underlying principles, reflects a methodological innovation that extends beyond optics. It exemplifies Newton's broader scientific philosophy: rigorous analysis, systematic experimentation, and the pursuit of universal principles capable of explaining diverse observations. In this way, his work in optics mirrors his achievements in mechanics and gravitation, demonstrating the unity of his approach to understanding nature. Newton's optical research also influenced the design of telescopes, one of the practical applications of his studies. Traditional refracting telescopes suffered from chromatic aberration, where different colors focus at slightly different points, producing blurred images. Newton addressed this problem by developing the reflecting telescope, which uses mirrors instead of lenses to focus light. This innovation not only improved image clarity, but also reduced distortion caused by chromatic dispersion. Newton's reflecting telescope allowed astronomers to observe celestial objects with unprecedented precision, providing a practical demonstration of how fundamental research in optics could directly enhance scientific instrumentation. Beyond his experimental achievements, Newton's work in optics had profound philosophical significance. By demonstrating that light behaves according to consistent, measurable principles, he reinforced the notion that nature operates according to discoverable laws. His research challenged traditional reliance on speculation, authority, or metaphysical explanations, emphasizing that careful observation, controlled experimentation, and logical reasoning are the keys to understanding natural phenomena. In this sense, Newton's optics exemplifies the scientific method itself, providing a model for how inquiry into complex problems can lead to clarity and insight. Newton's studies also laid the groundwork for future developments in physics. His analysis of light and color influenced later theories of electromagnetic radiation, wave, particle duality, and quantum mechanics. By establishing that natural phenomena could be dissected, analyzed, and understood in terms of fundamental principles, Newton provided a template for scientific investigation that continues to guide research today. Even the modern study of spectroscopy, which analyzes the absorption and emission of light by matter, owes its conceptual roots to Newton's pioneering work in optics. Equally significant was Newton's meticulous documentation of his experiments and results. He recorded procedures, measurements, observations, and conclusions in a manner that allowed other scientists to replicate his work, verifying findings and building upon them. This emphasis on transparency and reproducibility became a cornerstone of the scientific enterprise, fostering a culture of evidence-based inquiry and critical evaluation. Newton's approach demonstrates that transformative discoveries are not solely the product of insight, but also of rigorous methodology, careful record-keeping, and systematic testing. Moreover, Newton's optical research exemplifies his remarkable ability to integrate theory and practice. He did not separate abstract reasoning from hands-on experimentation. Instead, he allowed each to inform the other. Theoretical ideas guided the design of experiments, while experimental results refined and tested theoretical models. This iterative process of hypothesis, experimentation, and refinement became a hallmark of Newtonian science, influencing not only optics but his broader work in mechanics, gravitation, and astronomy. In conclusion, Newton's contributions to optics illustrate the depth, rigor, and originality of his scientific genius. By demonstrating that white light is composed of a spectrum of colors, developing the corpuscular theory of light, refining the study of refraction and reflection, and designing the reflecting telescope, he fundamentally transformed humanity's understanding of light and vision. His meticulous experiments, emphasis on quantification, and integration of theory and observation exemplify the scientific method and set a standard for future inquiry. Newton's work in optics not only resolved long-standing debates and improved practical instruments, but also reinforced a broader philosophical message. The natural world, no matter how complex, can be understood through careful observation, rigorous experimentation, and logical reasoning. In doing so, Newton illuminated both the mysteries of light and the path of scientific discovery itself. Isaac Newton's later life reflects not only the enduring brilliance of his scientific mind, but also the complex interplay of personal dedication, intellectual rigor, and societal recognition that shaped his remarkable career. By the time he reached maturity, Newton had already transformed mathematics, physics, and optics, yet his pursuit of knowledge did not wane. The later years of his life illustrate a transition from solitary exploration to public recognition, institutional influence, and the careful consolidation of his vast body of work, leaving an indelible mark on the history of science. Following the publication of his monumental work, Philosophiae Naturalis Principia Mathematica, in 1687, Newton's reputation as a leading thinker across Europe became firmly established. The Principia not only codified his laws of motion and universal gravitation, but also demonstrated the power of mathematical reasoning to describe the natural world with extraordinary precision. The scientific community recognized the revolutionary nature of his insights, and his fame spread rapidly. Correspondence with other prominent scientists, invitations to prestigious positions, and accolades from learned societies reflected the extraordinary impact of his work. Yet Newton, characteristically, often preferred solitude and careful contemplation over public life, dedicating himself to meticulous study and refinement of his theories. In 1696, Newton accepted the position of Warden of the Royal Mint, a role that marked a shift from primarily academic pursuits to administrative responsibility. Though it may seem a departure from scientific inquiry, Newton approached this position with the same diligence and analytical skill that characterized his research. He undertook a comprehensive reform of England's currency, combating counterfeiting and improving the quality and reliability of coinage. Newton's application of logical reasoning, investigation, and systematic oversight in the mint reflected the breadth of his intellect, demonstrating that his talents extended beyond theoretical science into practical problem solving with tangible societal impact. 2 years later, Newton became the master of the mint, a position he held for the remainder of his life. In this capacity, he continued to apply scientific rigor to economic and administrative matters, overseeing mint operations, standardizing coinage, and implementing measures to stabilize England's financial system. His work in the mint not only demonstrated his versatility, but also highlighted the practical utility of his analytical skills, showing that the principles of careful observation, precise measurement, and methodical reasoning could be applied far beyond the laboratory or study. Through these endeavors, Newton gained widespread respect, both as a scientist and as an influential public servant. During his later years, Newton also engaged deeply with intellectual pursuits beyond mechanics and optics. He devoted significant time to alchemy, theology, and biblical chronology, reflecting a lifelong curiosity about the nature of existence and the hidden laws governing both the material and metaphysical world. While these studies are often overshadowed by his scientific achievements, they reveal the depth and breadth of his intellectual engagement. Newton sought to understand the universe not only through empirical observation and mathematical analysis, but also by exploring questions of fundamental meaning and divine order. His work in these areas underscores the holistic nature of his inquiry, blending scientific, philosophical, and spiritual dimensions in a singular pursuit of truth. Newton's later years were also marked by extensive correspondence and intellectual exchange with other scholars. He communicated with leading scientists and thinkers of his time, including John Flamsteed, Edmund Halley, and Christian Huygens, discussing observations, theories, and methodological questions. These interactions, often conducted through letters and publications, facilitated the dissemination of knowledge and fostered the development of scientific communities. Newton's meticulous documentation, careful argumentation, and willingness to engage in debate reflect his commitment to rigorous reasoning and the collaborative advancement of understanding, even as he maintained his characteristic focus on precision and accuracy, recognition of Newton's contributions culminated in several honors. In 1703, he was elected president of the Royal Society, a position he held until his death. As president, Newton influenced the direction of British science, championing empirical research, methodological rigor, and the integration of theory with observation. He encouraged the publication of important discoveries, provided guidance to younger scientists, and fostered an environment in which careful experimentation and logical analysis could flourish. His leadership at the Royal Society illustrates his role not only as a pioneering researcher, but also as a mentor, administrator, and shaper of scientific institutions, ensuring that his legacy would extend beyond his own work. In addition to institutional recognition, Newton received personal honors, including knighthood by Queen Anne in 1705, reflecting the esteem in which he was held in both scientific and political circles. These accolades acknowledge the transformative impact of his discoveries on human understanding, demonstrating that his contributions transcended the academic sphere to influence broader society. Yet Newton remained modest in demeanor, often more concerned with the accuracy and integrity of his work than with public acclaim, exemplifying a commitment to knowledge for its own sake rather than personal fame. The intellectual legacy of Newton's later years is profound and enduring. His consolidation and refinement of earlier discoveries ensured that subsequent generations could build upon a coherent, systematic foundation. The Principia and his optical research provided models of rigorous reasoning, careful experimentation, and mathematical formalism that shaped the development of physics, astronomy, and engineering for centuries. Newton's approach demonstrated the power of universal principles, the predictive capacity of mathematics, and the necessity of empirical validation, establishing standards that remain central to scientific practice today. Newton's influence also extended to the philosophical realm. By demonstrating that natural phenomena, from falling bodies to planetary motion, could be described by universal laws, he provided a vision of a rational, intelligible universe. This perspective profoundly influenced Enlightenment thought, inspiring philosophers and scientists to explore nature through reason, observation, and experimentation. Newton's work suggested that complexity in the world could arise from simple, consistent principles, reinforcing a world in which human inquiry and understanding could progressively uncover the order of the cosmos. In the final years of his life, Newton continued to study, write, and correspond, remaining intellectually active and deeply engaged with scientific inquiry. Despite failing health and advancing age, he maintained his commitment to careful reasoning, observation, and the pursuit of truth. His enduring focus, discipline, and clarity of thought exemplify the lifelong dedication required for transformative achievement. Newton passed away in 1727, leaving a legacy unparalleled in its scope, rigor, and influence. He was buried in Westminster Abbey, a mark of the extraordinary esteem in which he was held, both as a scientist and as a figure of historical significance. In conclusion, Isaac Newton's later life illustrates the culmination of a career devoted to the pursuit of knowledge, the application of reason, and the integration of theory and observation. Through his roles at the Royal Mint and the Royal Society, his continued research in mathematics, physics, and optics, and his engagement with broader intellectual questions, Newton demonstrated a versatility, rigor, and depth of thought that remain exemplary. His legacy encompasses not only specific discoveries, but also methodological and philosophical contributions, shaping the practice of science and the understanding of the universe for generations. Newton's later years highlight the enduring power of curiosity, discipline, and rational inquiry, reminding humanity of the profound impact that one dedicated mind can have on the course of knowledge, society, and our understanding of the cosmos. Isaac Newton's life and work collectively represent one of the most profound influences in the history of human knowledge, shaping not only the course of science, but also humanity's understanding of the universe and our place within it. Newton's impact extends far beyond the specific discoveries he made in mathematics, physics, and optics. It encompasses the methodological, philosophical, and cultural shifts that his genius inspired. To appreciate Newton's full significance, it is essential to consider the multifaceted nature of his contributions, ranging from technical innovations and theoretical breakthroughs to the enduring influence of his approach to inquiry and understanding. At the heart of Newton's influence lies the systematic unification of knowledge. His formulation of the laws of motion and universal gravitation provided a coherent framework that explained phenomena both on Earth and in the heavens. By demonstrating that the same principles govern falling apples, cannonballs, and planetary orbits, Newton bridged centuries, old divisions between terrestrial and celestial mechanics. This unification was not merely a technical achievement. It transformed humanity's conception of the universe. The cosmos was no longer seen as a collection of disconnected phenomena, but as a single, intelligible system operating under predictable laws. Newton's insight fundamentally altered the way people perceived nature, demonstrating that complexity could arise from simple, universal principles, and that the universe was accessible to human reason. Newton's work in mathematics, particularly the development of calculus, provided the tools necessary for precise analysis and prediction of physical phenomena. By creating a mathematical language capable of describing continuous change, he laid the foundation for the quantitative sciences. Calculus allowed scientists and engineers to model motion, calculate areas and volumes, analyze forces, and predict trajectories. Its applications span every discipline of modern science, from physics and chemistry to biology, economics, and engineering. The development of these mathematical tools illustrates not only Newton's technical brilliance, but also his foresight in creating instruments that would enable future generations to explore the natural world with unprecedented precision. Optics, another domain transformed by Newton, further exemplifies the breadth of his contributions. Through meticulous experiments with prisms, lenses, and light, he revealed the fundamental nature of color and demonstrated that white light is composed of a spectrum of individual colors. He also developed the corpuscular theory of light and designed the reflecting telescope to address chromatic aberration. These achievements not only advanced the understanding of light and vision, but also laid methodological foundations for experimental science. Newton's approach emphasized careful observation, reproducible experiments, and logical reasoning, establishing principles of scientific inquiry that remain central today. His work in optics illustrates the integration of theoretical insight and practical innovation, a hallmark of his broader intellectual legacy. Newton's influence also extends to the methods of scientific investigation. He exemplified a disciplined, rigorous, and systematic approach to inquiry, combining empirical observation with mathematical reasoning and logical deduction. This methodology became a model for scientific practice, emphasizing the importance of reproducibility, precision, and the careful testing of hypotheses. Newton's integration of observation, experiment, and theory transformed the pursuit of knowledge into a structured, reliable process, laying the groundwork for modern science. By demonstrating that nature could be described through universal laws and predictable principles. He encouraged generations of scientists to approach problems analytically and systematically, fostering the development of empirical research across disciplines. Philosophically, Newton's work influenced how humanity perceives the universe and its intelligibility. By revealing that natural phenomena follow consistent, discoverable laws, he provided a vision of a rational cosmos where observation, reasoning, and experimentation could uncover the underlying order. This perspective had profound cultural and intellectual implications, inspiring Enlightenment thinkers to apply reason and empirical investigation not only to the natural world, but also to human society, politics, and ethics. Newton's demonstration that order and predictability underlie apparent complexity influenced ideas about rationality, progress, and human capacity for understanding, extending his impact beyond the realm of science into broader philosophical and cultural domains. Newton's influence is further evident in the generations of scientists, mathematicians, and engineers who built upon his work. Figures such as Laplace, Lagrange, Euler, and Faraday expanded on Newtonian mechanics and mathematical methods to develop celestial mechanics, fluid dynamics, and electromagnetism. James Clerk, Maxwell, and Albert Einstein would later refine and extend his principles, showing their applicability in new contexts while also revealing their limitations. The continuity of Newton's influence highlights the foundational nature of his contributions. He did not merely provide solutions to specific problems, but established conceptual frameworks and methods that have guided scientific inquiry for centuries. In this sense, Newton is both a pioneer and a source of enduring intellectual inspiration. The practical applications of Newton's discoveries also demonstrate their transformative effect on human civilization. Newtonian mechanics enables the design of bridges, vehicles, machinery, and infrastructure. Calculus facilitates engineering, technology, and economics. Understanding of optics underpins instruments ranging from microscopes to telescopes and cameras. Newton's principles have directly enabled advancements in transportation, construction, telecommunications, space exploration, and countless other fields, profoundly influencing daily life and human capability. By providing both conceptual understanding and practical tools, Newton's work bridges the gap between abstract knowledge and tangible societal benefit, illustrating the comprehensive scope of his impact. Newton's personal legacy extends beyond his scientific and technical achievements. His intellectual rigor, persistence, and curiosity exemplify the qualities of a transformative thinker. He pursued questions with patience, meticulous attention to detail, and unwavering dedication, often working in isolation yet always striving for clarity, consistency, and precision. Newton's life demonstrates the power of focused inquiry, disciplined thought, and imaginative reasoning in achieving breakthroughs that fundamentally alter human understanding. His example continues to inspire scholars, scientists, and students, serving as a model for intellectual courage and dedication. Culturally, Newton has come to symbolize the triumph of human reason. He represents an archetype of the scientific genius, someone capable of seeing hidden patterns, formulating universal laws, and systematically testing ideas to reveal the structure of nature. The image of Newton, whether under the apple tree or contemplating the cosmos, conveys the notion that curiosity, intellect, and diligence can unlock the mysteries of the universe. This symbolic legacy reinforces the broader societal value of science, education, and rational inquiry, influencing not only researchers but also broader public appreciation of knowledge and discovery. Finally, Newton's overall impact reflects the integration of multiple domains of human thought. His work transcended boundaries between mathematics, physics, astronomy, and optics, while influencing philosophy, methodology, and culture. The interconnectedness of his discoveries demonstrates the unity of knowledge, illustrating that breakthroughs in one field can have profound implications across others. Newton's intellectual legacy, therefore, is not limited to isolated achievements, but encompasses a comprehensive vision of the natural world and the principles that govern it, embodying the enduring potential of human reason and inquiry. In conclusion, Isaac Newton's overall impact on science and humanity is unparalleled in its scope, depth, and enduring influence. By formulating universal laws of motion and gravitation, developing calculus, pioneering studies in optics, and establishing rigorous methods of scientific inquiry, he transformed the understanding of the natural world. His work unified terrestrial and celestial phenomena, provided tools for precise prediction and analysis, and inspired generations of thinkers across disciplines. Beyond technical achievements, Newton's legacy encompasses methodological, philosophical, and cultural dimensions, demonstrating that the universe is intelligible, discoverable, and governed by rational principles. His life and work continue to inspire, guide, and challenge humanity, embodying the enduring power of intellect, curiosity, and disciplined inquiry. Newton's genius reshaped the way we perceive, investigate, and interact with the cosmos, leaving a legacy that endures as a cornerstone of modern science and human understanding.